Hello and welcome to the second part of structural instability and zero stiffness condition. My name is Surajit Ghosh, and in this session I will discuss about different types of structural instability, how to identify these problems in a model, and how to rectify the model to eliminate all these warnings. In last part, I have discussed about zero stiffness condition and its effect on the structure. Also, how to identify the problem by interpreting the warning message. You should go through the first part to get a complete idea about instability condition. An instability is a condition where the equilibrium criteria between applied load and reaction load is not satisfied, which creates several structural problems including large deflection, infinite time period, and complete structural failure. There are different reasons of instability which I will discuss in detail, but the primary reason is simple. Applied load on the structure is not able to make its way into the supports because no load path exists. Zero stiffness problem, which I have discussed in the first part, is one of the reasons for instability. Before going into the details, let's talk about the instability message which is reported in the output. Node number and direction of instability is reported here, similar to zero stiffness warning, but for instability, the direction is not mentioned as a number. Rather, the actual direction of instability is reported. Using this information, we can locate the portion of the structure where the problem occurred. Along with this, another note is reported. A weak spring is added for stability. Do you know why a spring is added to the model during analysis? When a load is applied in the zero stiffness direction, there is no stiffness present in the structure to resist that load. So, that portion of the structure will be deflected infinitely in the load direction, which leads to a calculation problem as it is not possible to handle this infinite deflection numerically, and results calculated on basis of this displacement value will be erroneous. To handle this infinite displacement problem, STAD adds a very weak spring in that zero stiffness direction to provide a very small resistance. This does not change any structural behavior, only reduce the infinite displacement to a numerical value. Thus, instead of an infinite displacement, a very large value of displacement is reported due to the presence of a weak spring. We can also check the instability location from the GUI. In the post-processing mode, under Layouts, instability option is available only for those models which has some issue, else it will be grayed out. Using this, we can highlight the problematic locations on the structure. Note that the location of instability is only an estimate based on the nature of the numbers in the stiffness matrix. Hence, it is difficult to pinpoint with accuracy. In general, the location that STAD reports is a part of the model which is rendered unstable due to connectivity problems. There are several reasons for instability condition. We can categorize the reasons either due to modeling problem or due to math precision problem. Modeling problems can lead to both local and global instability condition. I have already discussed about local instability in my previous video, which is limited to a portion of the structure. This might be due to the presence of truss member or member release specification. When we assign a truss or full release specification, zero stiffness condition appears, and if the load is applied in the zero stiffness direction, nothing can resist that load, which results large deflection. Also, the applied load cannot transfer to the support which creates an instability. This is what I have discussed in part 1, and this zero stiffness condition is one of the reasons of instability. Global instability condition occurs when the whole structure is not stable, which results a large overall deflection. This is not a local problem where only a part of the structure is affected. Rather, for global instability, the whole structure is unstable. Improper support assignment is one of the reasons. Also, improper connectivity between different structural elements like member to member or member to plate connection can create instability condition. If plates are not meshed properly, then those plates don't have proper connectivity with other plates and members, which results large deflection. You can check my previous video on finite element mesh generation for more details. Improper connectivity can create both local and global instability depending on the nature of connection. And finally, the MAC precision problem. This is caused by the numerical instabilities occur in the matrix inversion process. The reason is large variation of stiffness between the adjacent members. This variation can be resulted from intentional assignment of property values, like when we model a very high stiff or rigid member to duplicate the member offset condition. Incorrect unit assignment is another reason. I will discuss this in detail. First, let's talk about the instability condition due to the modeling problem. For this, I am going to use the same truss model that I have used in the first part. We know that this model has some local instabilities due to the truss member specification, and for load case 2, where the load is applied in the z direction, which is the zero stiffness direction. But this problem is limited to the truss level only, and there is no global instability. Now I want to change the support from fixed to pin support. For fixed support, degrees of freedom is 0 and the structure is restricted to move and rotate in any direction at the support level. But for a pin support, it can rotate about any axis at the support, as 3 rotational directions are not restricted for pin support. Analyze the structure. 18 warnings are now reported. Previously, it was 13 zero stiffness warning. Additional warnings are reported for instability condition at node 2, 15 and 23. Few nodes are reported. A very weak spring is added for stability to change the deflection from infinity to very large value. Check the displacement value for load case 2. It is in terms of 10 to the power 11, several kilometers of deflection. We can check the deflection diagram from post-processing mode. For load case 2, the deflected structure completely disappears from the screen, which is very normal with 1000 km of displacement in the z direction. This is a global instability condition which occurred due to the support condition. We have applied load in the z direction, but there is no rotational stiffness present at the support level for pin support. So the structure is free to rotate, and this creates a huge overall deflection which is not limited to a portion, but the entire structure is unstable. Coming back to the math precision problem. To understand this, once again we need to go through some basics. This error is reported when numerical instabilities occur in the matrix inversion process. One of the terms of the equilibrium equation takes the form 1 by 1 minus a, where a equals to k1 by k1 plus k2. These K1 and K2 are the stiffness coefficients of two adjacent members. Assume two conditions. Either a very stiff member is connected to a very flexible member, or the member properties are assigned in such a way that there is a huge difference of E or property value or member length. A common modeling mistake is to specify the dimensions in incorrect unit, like 250 meter by 400 meter sections, or even material properties and length of a member in wrong unit system. This results a large value of stiffness component. So K1 is very large than K2, and K1 plus K2 value is almost equals to K1. In such case, A value equals to 1. Hence, 1 by 1 minus A tends to infinity. For example, consider this type of property assignment. A large variation of stiffness between connecting members, which may cause instability problem. If you want to assign a very rigid member by assigning a large section or very high E value, you should check this condition. Till now, I have discussed about zero stiffness and local instability condition using truss and member release command. Also discussed about the global instability condition using a pin support example. To summarize, if there is any warning in the output related to zero stiffness or instability condition, we should check the statics check results to find whether there is any loss of applied loads. Also, we need to check the deflection values to find out if there is any large deflection in the model. We can check this information from the post-processing mode or from the output file by using the print commands. These two checks provide a preliminary idea whether the structure is unstable or if there is any other effect on the structure. On basis of the preliminary assessment, we need to further review the analysis results. There are also several conditions when we can ignore the zero stiffness or instability warning. If the external applied loads are not in the zero stiffness direction and equals to the reaction, if the deflection values are not excessive and within tolerable limits, in such case, we can simply ignore the warning and there is no need to change the model. These are treated as harmless warnings. But if these conditions are not satisfied, then the structure is unstable and we should rectify the model. Do you know how to resolve this issue and remove these warnings? The structure is unstable as there is no stiffness present in a particular direction. The solution is provide adequate stiffness in that direction. If we assign the member specification or support condition in such a way that there is some stiffness at all or loaded direction, then the structure will be stable without any large deflection, as the relevant stiffness will resist that applied load. How to do that one? Let's check the first model with local instability problem due to truss member with fixed support condition. In this model, we have declared all the members at root level as truss member so that these members can carry only axial load. In reality, it is almost impossible to maintain a condition where a member carries only axial load and all other force components are ignored. There must be some shear and moment transfer through the connection. So, we should consider the same during modeling. In place of truss member specification, we can specify the member as normal member and then release majority portion of the rotational stiffness using the partial moment release option, which is available in the beam specification page. Using this specification, we can declare that at start or end node of a member. Rather than fully eliminating the stiffness for a certain rotational degrees of freedom, we are willing to allow the member to have a small amount of stiffness in that direction. Advantage of this command is we can control the extent of the release or how much force will be transferred to the connecting member by specifying the percentage of release. The value must be in between 0 and 1. 0 means no release condition, where full force transfer is allowed, and 1 means full release condition. No moment will be carried or transferred from this member. We can release all three rotational stiffness components using MP option or specific rotational stiffness using MPX, MPY, and MPZ option. For a truss member, there is no rotational stiffness in any direction, so we can specify the MP value as 0.99 and assign this to the start and end of each truss member. MP 0.99 means the bending and torsional stiffness are 99% less than what they would be for a fully moment resistant connection. We have released 99% of rotational stiffness, and rest 1% stiffness might be adequate to allow the load to pass through the node from one member to other. In simple words, the difference between this release specification and member truss specification is only 1% stiffness, which is very small amount. But this can solve the zero stiffness or local instability condition arises from inadequate resistance. Now this model does not have any truss member. We have replaced that with partial member release command where 1% rotational stiffness is allowed. Analyze the model. There is no warning message. Previously, there were 13 zero stiffness warnings. Watch the first part of this series for more details about this model. In the post-processing mode, check the static check result for load case 2, which was applied in the zero stiffness direction. Applied load and reaction force values match. Also, the deflection value is well below the tolerable limit. Now, check the moment value in the truss member. It is very small and does not have any significant effect on the member design. This small amount is acceptable for an axial member. With this modification from member truss to partial moment release, the problem of local instability due to truss member is now fixed. Let's check another model. This is a frame model where full moment release is assigned to these beam members. The intention is to create a shear connection between these members. That's why all the rotational stiffness are released to eliminate any moment transfer. Two loads are applied on this structure. Self-weight under load case 1 and load from the x direction under load case 2. After analysis in the output file, an instability message is reported for joint 9 in the fx direction. There is also a note about inclusion of a weak spring. As per our discussion, first we need to find out whether this is harmless or there is any effect on structural stability. From the post-processing mode, we can confirm that the applied load and reaction for load case 1 is same, but there is a difference for load case 2 for Fx, My and Mz. Next, we need to check the deflection values. For load case 1, all deflections are negligible. But for load case 2, where the load is applied in the x direction, large deflection is reported in the same direction. This suggests there is a problem in the model for load case 2 and we should rectify this model. Check joint 9. This column is pin supported, so it can't resist any rotation at support level. Connecting beam members don't have any moment resisting stiffness due to full moment release, and load is applied in the lateral direction. So due to lack of resistance in the load direction, this frame deflects out of the screen. We need to rectify this unstable condition. There are multiple solutions. We can resist this lateral movement by introducing bracing member like a cross bracing or partial bracing, or change the support condition. For this model, this type of arrangement is not feasible due to the project requirement, and we need to consider some other options to resist this deflection. One good alternative is to assign some stiffness at the beam column junction. Similar to previous model, here also we can allow 1% stiffness by specifying partial moment release command with value 0.99. Previously, it was full moment release, and this time we are allowing 1% moment transfer. With this small change, reanalyze the model. No warning is reported. That means instability problem is now fixed. But we should check the deflection and static check results for load case 2. Static check results are okay. No difference in load and reaction values. But the deflection value is quite large, almost 3 inch. So from displacement point of view, results are not adequate. We can further modify the stiffness value to reduce the deflection in x direction. This will obviously increase the end moment, and we need to consider that during design. This time, I want to increase the rotational stiffness from 1% to 2%. So MP is now 0.98 at both ends of the member. Reanalyze the model. We know the structure is stable, so no warning is reported. From the post-processing, we can review the deflection in x direction, which is around 1 inch. Check the moment value for all the members. Highest value is around 14 kN meter. I think this is acceptable for a CR connection. We can further reduce the deflection. This time, I am going to change the MP value to 0.96. 4% rotational stiffness is allowed at both ends of the member, and reanalyze. Let's check the deflection value for load case 2. It is now 16 mm only, quite low than previous trial. Highest moment value is still around 14 kN meter. We need to consider this moment value during CR connection design. Assigned connection must have at least 15 kN meter moment carrying capacity. This model seems fine now. We can follow this approach for any unstable structure. Review and change the stiffness value to optimize the deflection and force values in a structure. This is all about instability and zero stiffness condition, how to identify and rectify the problems. Just one last information. All these three models are part of a real structure, not some demo model. I have isolated a portion of a warehouse building which was structurally not stable to demonstrate the reasons and solutions. It is better to use simpler structure at the beginning for demonstration purpose. There are several other reasons of instability, which I will discuss in the next video using several real-life models, and also cover how to rectify those problems using different approach. Stay tuned and keep watching.